Okay. Oh, well, not yet. Ready for the exam? Hmm? No? At all? Nothing? Not even a little bit?
Oh, I'm like not ready to take it, but like I'll be there. Physically, I'll be there, but mentally, it's a gamble.
So I don't know why, but this class, like physics 112, 113, like I remember when I started teaching this class, maybe like 5, 6 years ago, like the ratio between men and women was close to even. There was always been more women students, but this year it's insane. Like it's like a 95% of the students are women, and only like there are only like 2, 3 students that, well, more that they are male students. So I don't know what's been. Are you guys kicking out the male students? Or just get out of here? I don't know. It's kind of weird. Okay, so one thing that I want to do today is I want to go through the homework, make sure that everybody understand everything on the homework, especially that problem with the spine. I think everybody has questions about that, or many people have questions about that. The one with the head, it's also kind of tricky. So we'll do those two. Well, and if you have more questions, then we can do more. There's another exercise that I want to go through. So I'll make sure that we have time for that. And just to remind everybody, we have a test on Friday, just in case you were not aware. Kennedy, you knew that you have an exam on Friday? Yes? Are you ready?
No.
At all? Not even a little bit?
No.
Oh. So the way the exam is going to work is that trying to be. Oh. So the way the exam is going to be is that I'm going to open the exam probably on Friday around 8:30. And I'm going to open that exam and it's going to remain open until Saturday midnight, something like that. So you have almost, it's less than 48 hours, like 40 hours that you can pick when you can do the exam. Once you start the exam, you're going to have 2.5 hours to finish it. I haven't done the exam yet. I mean, I haven't. You're eating candy, gum. Is it gum? It's a mint? Oh, I don't like mints. If it were a gum, I would ask you for a gum, but I don't like mints. Sorry. So you're gonna start the exam, and then you're gonna have 2.5 hours to finish that exam. I haven't done the exam yet. I haven't finished it, so I don't know exactly if it's gonna be 2 or 2.5. There are gonna be 5 questions, probably, and it's gonna be a mix of concepts with problems. It's probably gonna be 2 concept questions and then 3 problems. So it's gonna be probably that configuration. On the problems, you're gonna have a chance to put your answer on your test, so you can put the numerical answer of the question, and when you submit the problem, you're gonna be able to see if that was the right answer or not. but the right answer is just gonna be like maybe 20% of the grade for that problem. I'm gonna ask you to submit your worksheet so I can see how you solve the problem, and that's gonna be the big chunk, okay? So even if you don't have the right answer, I don't think that is you screw completely. Sometimes if you didn't make a good conversion, or if you forgot to multiply by a sign, or you did many or just little details, it can affect your grade. It can affect your result, but that doesn't mean that you did everything wrong. And personally, I care more about the process, that you do the free body diagram, that you can set up the equations, that you understand what you're doing. And if you screw up in the algebra, it's not a big deal for me. The exam are going to be similar to the homework problems. So yeah, it's gonna be something like that. So I'm not gonna ask something that we haven't seen. I'm not gonna ask you something that we have specifically. I'm not gonna ask you anything that any of the same problems that we can see in class. Similar to those, but not exactly the same. Okay, so a 40-hour window to start the exam. Once you start the exam, 2.5 hours. When you're done, submit your paperwork. Okay. I will have the grades for your exam. I'm gonna try to have them by Wednesday of that week. So I'll try to have them as soon as possible. And once you have your answer, your grade, then we can talk about if you want a second opportunity to do the exam again or anything else, and we can do reviews and all that stuff. Okay. Make sense in the chat? Okay, so perfect. Okay, so I'm gonna just talk a little bit about moment of arm that I think is a little bit confusing. So I'm gonna try to explain it in a different way and see if that makes sense. Okay. So when we talk about torque, we usually want to see. I'm going to assume that I have this rod, this beam, can be your arm, can be a leg, can be anything. I'm going to have a pivot point, and I'm going to have a force. And in this case, I'm going to assume there's a force caused by gravity, or they're just pulling down. I'm going to have this angle over here. And the way I calculate torque, if I know that this angle is going to be phi, the way we calculate torque is you say, okay, I'm going to look at the distance from the pivot point to whatever that force is. And this distance is r. So I'm going to look at that distance. And then I'm going to multiply by the perpendicular force that I'm applying. I want perpendicular to what? Well, perpendicular to the arm, perpendicular to this axis of rotation. So in this case, I want the force that goes in this direction. Okay, perpendicular to this guy. So if this angle is phi, then this will be r f sine of phi. Okay? And that's usually the way we've been calculating torque. Now, there's a different ways that you can think about torque. And it says, okay, the way I'm gonna calculate torque, I'm gonna have the same pivot point. I'm gonna have the same distance here, and I'm gonna have the same force and the same angle. So everything is exactly the same thing. Now, instead of looking for the perpendicular force, what I'm gonna do is I'm gonna find the shortest distance between the pivot point and the force. The shortest distance is always going to make a 90-degree angle with the force. If I extend this force, I'm going to look at the line that makes 90-degree angle and that connects the pivot point. And this is going to be the shortest distance. Okay, I'm going to call that R perpendicular because it's perpendicular to the force. So the way we calculate torque will be, okay, I'm going to look at the perpendicular distance times the force. Now, how can I calculate this perpendicular distance? Well, if I look at this triangle rectangle and I look at my angle phi, well, sin of phi is going to be opposite over hypotenuse. And in this case, the opposite side is the R perpendicular. And the hypotenuse is going to be R. So R perpendicular is going to be R sin of phi. So I can substitute here and I can have torque R sin of phi times the force. And you can see that these two equations are exactly the same. Okay, so these are perpendicular. This is what we call the moment of R. For the moment R. Yeah, does it make more sense? Is it a little bit better? Ish? Alexis? No? It's better? Are you sure? Okay. Okay, so if it doesn't make any sense why the formulas look a little bit different between when you work with moment of arm that when you're working with a perpendicular force, they're there's exactly the same force. It's just you reach to that force. It's exactly the same equation. You just reach that equation with a different concept. And in some cases, working with this perpendicular distance is easier than working with the perpendicular force. And we're going to see a couple of examples. Okay. Questions about the homework? Yes, Mary?
Can you do number 66?
66.
The one with the head.
The one with the head?
Yeah.
Okay. 66. Let me find it. 66. Okay. So, problem number 66. You have the head. And the head, we're going to have a center of gravity of the head, which I'm going to assume there's somewhere around here. We're going to have the muscle that connects to your neck and the spine. So that's going to be somewhere around here. And we're going to have the pivot point. And the pivot point, I'm going to say there's going to be somewhere around here. Okay, so we're going to have three forces. We're going to have the weight of the head pulling down. We're going to have, so this is the weight of the head. We have the force of the muscle. And here, we need to have a reaction force. Okay, so here, we're going to have a reaction force. I'm not going to call this FR. We're not going to do much with the reaction force in this example, but every time you have torque problems, think that there's always going to be a reaction force. And in some cases, it's actually more important than the torque. Okay, so we have a couple of distances over here. So we know that the vertical distance between the center of gravity and the pivot point, that's going to be 10 centimeters. The horizontal distance between the pivot point and the center of gravity is 4.2 centimeters. And the the horizontal distance between the pivot point and the muscle, this is 5 centimeters. Okay, and what we want to find out is what is the force of the muscle that keeps the head in balance. So a way that you can try to find it, I'm just going to draw a line between the pivot point and the center of gravity of the head. I'm just going to go like this. Erin, you've fallen asleep.
Sorry.
I saw you yawning. You think you can trick me with a mask, but no, I see the jump. That's okay. So I have the pivot point here. I have this reaction force, and I'm gonna put my my frame of reference. I'm gonna put it here. I'm gonna put it there, so that way I don't care about the reaction force. Regardless of the magnitude, it's not gonna create any torque. Now the head, the weight of the head is gonna go down. And even though I don't have the distance between the pivot point and the center of gravity, even though I don't have this distance, and I don't have this angle over here, but I have this distance. And that's my definition for perpendicular distance. That's my definition of moment arm. Okay? This is gonna be my 4.2 centimeters. So I can calculate what is the torque of this force by multiplying the force of the head, the weight of the head, times this perpendicular distance, this 4.2 centimeters. And something similar is between the muscle and the pivot point. Okay, so this is one example in which, even though we don't have all the information, just because of having that horizontal distance, we can solve for torques. So I'm going to have all the torques equals to 0. The torque of the muscle, the torque of the weight of the head is rotating the head counterclockwise, so that's going to be positive. And the weight on the muscle of the head, this one is going to rotate clockwise, so this is going to be negative. So I'm going to have 0.042 times the weight of the head, and the mass of the head is 5 kilograms, no less than 4.8 times 9.8. I think it's 4.8. Minus, oops, sorry. I forgot. Oh yeah, distance. 4.5 centimeters times the force of the muscle, and that's what I want to find out. I want to find out what is that force of the muscle. So from there, I can solve for the muscle. So I'm gonna have 0.5 and you end up with and this is just a linear algebra, and from there you can find the force on the muscle. What do you got?
I got 39.51.
39.5 newtons. Okay. Make sense? Now, I'm gonna rotate the head. I'm gonna let you guys finish copying this. Any questions about this? Oh, okay. So now what I'm gonna do is I'm gonna rotate the head, and I'm gonna see what is the force of the muscle when the person is lying down on his or her stomach, and try to see if that changes the force of that muscle. So what I'm gonna do, now this guy is gonna be looking down. The center of mass is gonna be in the same place. This doesn't change. I'm gonna have my pivot point, and I'm gonna have the force of the muscle here. Now, gravity is still gonna be pulling down, so this is gonna be now the new direction of the force of the head. Okay, so now I need two distances. I need this distance between the center of gravity and this pivot point. And I know that this is gonna be 10 centimeters. And I know the distance between the muscle and the pivot point, and that one doesn't change. So this is still gonna be 5 centimeters. And if you have trouble seeing this, you literally can grab the book and just rotate it 90 degrees, and you can actually see those distances. The muscle doesn't change position, so it's gonna be horizontal now. But gravity technically doesn't change either. It's still gonna be pointing down. It's just how relative it is with the position of the head that is gonna be different. So I'm gonna do the same. I'm gonna have the sum of torques has to be equal to 0. The weight of the head, you can imagine that if my pivot point is there, the weight of the head is kind of rotating counterclockwise. So this is still going to be positive. And the muscle is kind of rotating my head in the opposite direction. So this is going to be negative. So here I'm going to have minus 0.1, 4.8 times 9.8, not plus, sorry, minus 0.05 and the muscle equals 0. And again, solving, I'm going to do it step by step. Again, this is just algebra. We're trying to solve for that f sub m. And you end up with 90 something, 92?
94.1.
94.1 newtons. Yep. Yeah, makes sense. Any questions about this problem? No. Any other problem with the homework? Yes. 56? 52. Which one is 52? Okay. So 52, we have a beam with a guy sitting there, and we have a cable pulling up. Okay, so we know that this distance is going to be 6 meters. The person
The person is going to be 2 meters from the edge and has a mass of 80 kilograms. And the beam has a mass of what? 1,450 kilograms. Now, the maximum tension that we can have is 15,000 newtons. Okay, so what we need to do is to find out if this tension that I have here, I want to find out the tension, this tension here, and I want to find if the tension is bigger than the maximum tension, then the guy is dead. Okay, so that's basically what I want to do. I want to save this person's life. You see, physics is important. You can save people different ways. Just say. So what I'm gonna do is I'm gonna do an equilibrium problem, and I'm gonna solve for t, and then I'm gonna compare it against the maximum value. So I'm gonna have my free body diagram. I'm gonna place my point of reference at one of the edges. The reason why I'm gonna do that is because even though the problem doesn't say anything, here we're gonna have a reaction force. And this reaction force comes from the normal force that we have because we have a contact between the beam and the wall. So there's going to be a reaction force there. And you can also imagine that there's going to be a friction force between the wall and the beam that prevents the beam to being displaced vertically. So there's two forces, and this creates a reaction force. So because I want to ignore the effects of torque because of this, I'm going to put the reaction force at that point. And Sylvia, yes, I can do 68 after this. So I'm going to have the force of the weight of the beam is going to be 3 meters from the edge. This is the weight of the beam. And this is going to be 1,450 times 9.8. We have the weight of the person, 4 meters from the edge. So this is going to be 3 meters. This is going to be 4 meters. And this weight is going to be 80 times 9.8. And then we're going to have this tension at a 30-degree angle. Okay. That was a big one. Alexis, it was you? It was you. Okay, so we want to find out what is the torque because we want to save this guy, or we're going to assume that the beam is not moving. So I'm going to look for the conditions of equilibrium, and I'm going to have this torque caused by the weight is rotating clockwise. So this is going to be negative. The torque created by the weight of the person is also going to be negative. And the perpendicular force of this tension is moving clockwise, counterclockwise. So this one is going to be a positive torque. Okay, so I'm going to have the torque of the tension plus the torque or the weight of the beam plus the torque of the person has to be equal to 0. The torque of the tension, and I'm going to do it down here, is going to be 6 meters. And then the perpendicular force is going to be the tension, which is the one that I want to find out, sine of 30. And this is going to give me the perpendicular component. Positive. Then the weight of the beam is going to be 3 meters times the weight, which is 1,450 times 9.8. And then the torque created by the person will be 4 meters times 80 times 9.8. The angle of these two guys is 90 degrees, so it's not that there's no sine, it's just that the sine of 90 is 1, so we don't write it down. And sorry for the tension. I'm just going to do it again, just step by step. And from here, I'm going to end up with that. And Martina, what you got?
I got 15,255.
15,255. You killed the guy?
I killed him too.
How much?
I said I killed him too.
You killed him too?
So, yeah.
Holy, wait. Kenny, did you kill him? Really?
He's so dumb.
Yeah, he's dead. So I get a tension of 15,255. Holy crap. Newtons. So the tension that we found out is larger than the maximum tension, so he's dead. So, Rihanna, not sure what we did earlier today. I thought we saved him. No, we killed him. Oh, I just didn't care enough. So sad. 68. I'll do 68, and then we'll do something different. 68. Okay, 68 is kind of tricky because we don't have a distance for the spine. We just have relationships between the insertion points. I don't know what's that. So we have a person that is going to be bending his back at the waist, and we know that we have a center of gravity for the weight of the arms and the head. That's going to be kind of where the neck is. Then we're going to have a center of mass of the torso. That's going to be somewhere around here. And then in between those two center of mass, we have this muscle of the spine that's pulling up. That's kind of keeping everything in place. Okay, the pivot point is going to be at the waist. And there's another force that is that reaction force. And we'll talk a little bit about that later. The problem doesn't mention it and it doesn't ask you to calculate it, but I want to talk about this a little bit later. So distances. So the length of the spine is going to be L. So this distance is L. Where the torso is L half. It's L over 2. And where the muscle is inserted that is 2/3 of L.
Okay, now weights. We have
The weight of the torso to be 320 newtons. The force of the weight of the head is 160 newtons. And we want to find out what is the force of that muscle, okay? So, again, what I have is equilibrium. So I'm gonna have all the torques are gonna be equal to 0. So that means that I'm gonna have the torque of the torso plus the torque of the head plus the torque, sorry, the torques of the torso, the head, times the muscle plus the muscle have to be equal to 0. I'm putting my frame of reference at the hip, so I don't care about the reaction force or the torque created by the reaction force. So the torque of the weight of the torso and the weight of the head, these are going to create a negative torque, and the torque of the muscle is going to be positive. Okay, I hope you can see that one. So the torso is going to be distance to, oh, I need an angle. What is that angle? 30 degrees. This angle is going to be 30. So that's going to be 1/2 of L times 320 sine of 60. Yeah. So you can imagine if I have the weight of the torso and this angle is 30, this is going to be 60. So I need the perpendicular component. So I'm going to need that one. Okay, so that's why we have sine of 60. Okay. Oh crap. And that one is going to be negative. The torque of the head is at a distance L, so that's going to be L times 160 sine of 60. Okay, and the last one is going to be the torque of the muscle. That's going to be at 2/3 of L. I don't have that value of the force, but here, if I draw it again, this is going to be my pivot point. I know that this angle is going to be 30, and this force is going to go like this, and this angle is 12. And we know that because of the problem. I think that's part of the data of the problem. So this is going to be 12 degrees. And the angle that I care is the angle between the spine and the muscle. So it's literally going to be that. So here I will have sine of 12. Okay, and the sum of all these have to be equal to 0. So I'm gonna write it down a long way. So I think it's gonna be easier to see. So I'm gonna have 1/12. Okay, now notice that on the left side, all the terms are multiplied by L. So I can divide both sides of the equations by L, and I basically am going to cancel L. So it really doesn't matter the length of the spine. What it matters is where is the relationship between the length and where they are, where the different forces are located. So all these L's, I can cancel all those L's. So I'm going to have minus 1/2 of 320 sin of 60 minus 160 sin of 60 plus 2/3 Fm sin of 12. And again, I'm solving for that force on the muscle. So I'm just gonna try to solve it. I'm just gonna do a little bit of algebra here. Okay, 1/2 times 320, that's gonna be 160. So I'm gonna have 160 sin of 60 plus 160 sin of 60. So we just have two of the same, so this will be 2 times 160 sin of 60. And on this side, I'm gonna have, oh, this is 2/3. 2/3 sin of 12. Okay, this is just a little bit of, yes, oh, sorry. Sorry. Yeah. Solving for this cancel with this one. Oh, wait. I get pretty much 2,000 newtons. It's like 1,999 point something. Okay. Now, if you look at the forces that are here on this spine, so you have the spine, you're gonna have this force that is 2,000 newtons pulling in this direction. Then you have the weight of the torso pulling down, and you have the weight of the head also pulling down. And again, the perpendicular component is the one that's creating the torque. So this force over here creates torque. This force over here creates torque. That one over there creates torque. Those are the ones that create the torque. But there's another component, and that component, in all cases, is pointing towards the pivot point. So this one is here. This one goes here, and you have another one that's also go here. So you're gonna have a reaction force here at the pivot point. That's basically going to try to match all of these three forces, so the spine is in place. So as a consequence, that's a compression force. And that compression force, if it's too big, that's the one that's basically gonna dislocate your discs. So even though the problem doesn't ask you to calculate that reaction force, you can try to do it, and actually that would be a good exercise to practice for the exam. But this force is really, really big. That's gonna be probably bigger than those 2,000 newtons. That's the one that actually creates the dislocations of discs, this reaction force. Okay. Any questions? Okay. Okay, so Emma is asking, on problem 66, why did we not use gravity for the 0.05? Oh, sorry, Emma, I didn't see you. This is the second time you asked this question. I didn't see it the first time. 66B, Emma? So we don't use the force here. We don't multiply in this part. I think this is what Emma is asking. So when we are solving for the force, we're not multiplying by 9.8. So Emma is asking, well, why don't we use 9.8 here, but we're using it here? And so this 4.8 times 9.8, all this is the force of the head. And it's caused by that mass of the head that's pulling down. This force over here is the force created by the muscle. So we just want to know what is the value in newtons of that force. So there's no mass associated to that force, it's just the strength of the muscle. Make sense, Emma? Yep. Cool. Any questions? No? Larry? Cool. Okay. So over here, it's a very classic diagram of the different kind of techniques to do squats. And I think most of you that are athletes or that have done any kind of physical activity at one point in any kind of competitive sports, they use a squat. Like it doesn't matter if you play golf or video games, that they still ask you to do squats. Don't ask me why. For the video games. For the rest, I understand why. But there are different techniques to do a squat. The three that are more common is, and everything has to do with where you place the barbell with respect of your body. So the first one is under your chin, the other one is behind your back, and the other one is lower on your lower back. Well, almost lower than the neck on your back. And the main effect that you have is that the angle that your spine has with respect of the ground is gonna change. So when you have your barbell close under your chin, your back is a little bit straight. That compare when there's a lower below your neck, the bending of your back is gonna be bigger. Okay. The reason that you need to change that angle, and you need to change that angle, is because when you're doing squat, the position of the barbell and the mass of the barbell is significant with respect of your body weight. In some cases, the barbell can be a couple of times your own weight. And because it's really high, you have a very high center of gravity for that position. And remember that one of the conditions for equilibrium is that your center of gravity has to be above your base, in this case, your feet. So if you move this barbell even a little bit, if you don't have your back straight, you're gonna be away from that center of gravity for that base, and you're gonna fall. And you're gonna feel like you're gonna fall. There are some people that they do the squats on the toes, and they kind of lift their heels. And basically what they're doing is creating a more unstable position, because now your base is going to be narrower. So if you want a more stable, you need to put the heels on the back and the foot, and that gives you a wider base, and then you can have a little bit more wiggle room to position your body, especially if your core is not very strong. That can affect you. Now, one of the things that you want to do with the squat is that you want to strengthen the glutes, so you want to strengthen the quads, so you're going to strengthen the core, you want to strengthen the back and different muscles. So the ones that you want to do is, okay, how much stress or how much activation you have in different kind of and the different kind of muscles. One way that you can try to do that is by calculating the torque on a joint. So if you know the torque at a joint, like if you know what is the torque that you have on your shoulder and you know the insertion point of your deltoid, you can calculate the activation of that muscle. Or if you have someone that's compromised on the knees or on the hip, you don't want to give that person the exercise that's going to make that person have a higher torque or high stress on the knee. So you calculating the torque can help you evaluate that, or at least get an estimate. Now, measuring these angles that I have here is really hard in real life. Like there's not an easy way that you can measure these angles. The only way that you can do it, but it's not easy. You will have to set up the camera, have the camera perfectly horizontal to the ground, have the person take do the squat, take the picture, and then maybe print it and do this on paper, or maybe put some markers on the person and the different joints, ask the person to do the motion, and then evaluate. That's one way. Another way is to measure the distance of where the barbell is with respect to the joint that you want to analyze, in this case, the hip, and place a plumb in the barbell, and then just let that plumb fall. And then what you do when the person is in position, or the position you want, is just measure this distance, the distance from the joint to that plumb, to that vertical line. And you can do it with the with the hip. You can do it with the knee. You can do it with the ankle. You can do it with any joint that you want. Okay, and then you can see that, for example, in this case, the distance, this perpendicular distance between the knee and the plumb is way shorter than the distance from the hip. I'm going to draw it over here. So something like that. Here you have something that looks more or less the same. Okay, so these are perpendicular distances. All these are perpendicular distances. So if you have the same weight, you can see that the torque of this guy is going to be way smaller than the torque for the hip. And you can see here that the torque on the hip and the torque of the knees are going to be more or less the same, just by looking at these distances without doing any calculation. So you can say, okay, if you're doing a lower back squat, the torque on your hips is going to be way bigger than the torque on your knees. For the same mass, from the same weight, just by changing that position, you increase the torque on your hips. If you put your torque in front of your chin, your back is going to be straighter, so you're going to have higher reaction forces on your spine than when you have a higher angle. So just by looking at those changes, you can do an estimate of the effect of position of weight. Okay? Come on, that's cool. This is cool. No? Mary's saying that it's not cool. She's bored. She's ready to go. She's not saying that, but she's thinking about, and just because she's not refuting it, is accepting it. Any questions? Kennedy, it's cool. You see? That was it. That's all I asked. She said, yeah, sure, it's cool.
She's lying.
I don't care. Lie to me. Yes, don't make me feel bad or, okay. Questions?
Well, now I feel bad.
Any questions? Okay, so tomorrow I'm not gonna be on campus, but if you have any questions, if you want to go through any review, just send me an email. I'll respond it, and we can set up office hours. On Friday, there's no class, but I'll be here. So if you have a question, if you want to go through something before you start your exam, please let me know. And same thing, just send me an email and we'll do it. Okay?
Have a good day, everybody. No matter what Mary says, this was pretty cool. The what?
It's due at 5, but I have this, then lab is practice. So the homework is the phone. What phone?
The homework, you can upload it on,
Is it due at 5? Is it due at 5?
I think so, yeah.
That should be fine.
I have a couple more questions on the homework. You have office hours after this, right?
No, you should, yeah.
I have class till 2:10 though. Will you be here after 2:10? If you're not, that's okay.
You have class right now?
Yeah, until 2:10, like 1:10 to 2:10.
Oh, man.
I usually go and pick up my kid.
Okay, that's totally fine. What if I send you an email?
That would be great.
Does that work? Okay,
What problem are you, which one?
hold on. Let me-
No, it's physics, yeah. You have to do full
Okay,
rep for,
one was
the lab that we did last week.
number
What?
11.